Dark matter. What is dark matter? The simple answer to that is no one knows. But we know it's there, and we also know that it actually makes up about 85% of the mass of the universe. While it doesn't emit, absorb, or reflect light, we know it's there because of how its gravity affects things we can see. Galaxies spin faster than they should based on their visible mass, and the way the universe is structured only makes sense if there's a lot of invisible matter helping to shape it. Dark matter may hold the key to understanding how galaxies form, how the universe evolved, and even what it's made of at the deepest level. So how do we know dark matter exists? Galaxy rotation curves. Stars at the edges of galaxies move faster than expected, which suggests there's extra, unseen mass, helping keeping those stars from flying off into space. Gravitational lensing. Einstein's theory says massive objects can bend light, called gravitational lensing. As light from distant galaxies passes near dark matter, its path is warped. By studying this distortion, astronomers can map the distribution of dark matter in the universe. The cosmic microwave background. The cosmic microwave background shows tiny temperature differences that reveal how matter was spread out after the Big Bang. These patterns only make sense if dark matter was already there, helping regular matter come together. Large-scale structure of the universe. Computer simulations of the universe's evolution show that galaxies and galaxy clusters form the way they do only if there's a huge amount of dark matter. Without it, structures would be much smaller and more scattered. What is dark matter made of? There are several leading theories about what it could be. WIMPs, weakly interacting massive particles. They would have mass and interact via gravity, and possibly the weak nuclear force, but not with light or electromagnetism, which would make them invisible. Axions. Axions are ultralight particles that could exist in large numbers and act like a cold, invisible fluid throughout space. Neutrinos. Neutrinos are ghostly particles that barely interact with matter. Neutrinos would be even more elusive than regular neutrinos, and if they exist, they could account for some or all of dark matter. Primordial black holes. Some scientists have considered that dark matter could be made of tiny black holes formed in the early universe. Dark energy. Dark energy is just the name that astronomers gave to the mysterious something that is causing the universe to expand at an accelerated rate. It is often described as a kind of negative pressure pushing space outward, but it's unclear if it acts like a force at all. There are several main theories about what it could be. Vacuum energy. Some scientists think dark energy might be a constant energy filling space. This idea connects to Einstein's cosmological constant, which he later abandoned after the discovery that the universe is expanding. However, when it was later found that the universe's expansion is accelerating, the cosmological constant was reconsidered. Vacuum energy, arising from quantum fluctuations and virtual particles, might be driving this acceleration. There's a major issue with the vacuum energy idea. Calculations predict it should either be too strong, preventing galaxy formation, or not exist at all. Quintessence. Some scientists propose that dark energy is a dynamic energy field that fills space and acts opposite to normal matter, possibly changing over time and space. This idea is called quintessence, named after the ancient Greek concept of a fifth element. Quintessence might combine dark energy and dark matter, though they're usually seen as separate. Space wrinkles. Dark energy could be a flaw in the universe's structure, like cosmic strings, a flaw in general relativity. Some scientists believe dark energy might not exist, and that Einstein's theory of gravity may need adjusting on large scales. One idea, unimodular gravity, could explain the universe's expansion without needing dark energy. We still don't know what exactly is causing the acceleration, but it is present in the room with you as you read. The WOW signal. On August 15, 1977, the Big Ear Radio Observatory detected a powerful 72-second radio signal, later dubbed the WOW signal. The signal came at a precise frequency with no clear natural cause, leading to speculation of an artificial or alien origin, but it was never detected again. A new study by Abel Mendez suggests a magnet flare hitting a hydrogen cloud could explain the WOW signal. Despite being only a speculative but intriguing, says co-author Kevin Ortiz Ceballos, The WOW signal's narrowband nature and its occurrence at 1420 MHz, a key SETI frequency linked to neutral hydrogen, made it stand out. This frequency is often targeted in alien signal searches because it is universally significant and protected from human interference. The WOW signal was unusually strong and came from near-star cluster M55. Mendez's team later found weaker, similar signals, suggesting such natural events may be more common. Hydrogen masers exist in space, but none have been observed at 1420 MHz, and the required conditions for this to occur naturally are thought to be highly improbable. Many scientists still think the WOW signal was likely human-made interference, not aliens. Even Mendez doubts an extraterrestrial origin. The Fermi Paradox. In 1950, the Italian-American physicist Enrico Fermi asked, "Where is everybody?" during a lunch, questioning why we haven't seen signs of aliens despite the high chance they exist. He wondered, given that our planet was relatively young compared to the universe, we might have expected someone to have visited us by now. But we had no evidence of that ever occurring. Fermi died in 1954, just 4 years after posing his question, but his idea inspired entire fields of research, including the search for extraterrestrial intelligence. What are the solutions to the Fermi paradox? The most obvious and likely solution is that we simply haven't looked hard enough to find other life, and interstellar travel between stars is difficult. The first planets beyond our own solar system were only discovered in the 1990s. We found a few planets like Earth, but the distances between star systems are enormous, making journeys between them difficult. Our closest star system, for example, Alpha Centauri, is 4 light-years away. The distance from Earth to Neptune, for comparison, is 0.0005 light-years, a journey that would still take us decades with current technology. Some possible explanations. We're rare or alone. Life may be extremely rare, and Earth is a unique exception, or intelligent life might be even rarer, or self-destructive. They're avoiding us or don't care. Advanced civilizations may be following a prime directive, avoiding contact with less advanced worlds. They're already here, or we missed them. UFOs or unexplained phenomena could be evidence, though no solid proof exists, or civilizations may have visited Earth millions of years ago, long before humans. They're too far or too different. The distances between stars are vast. Communication or travel might be impractical, or they may use technology or communication methods we don't understand or can't detect. We're early. Maybe we're among the first intelligent civilizations in the galaxy. Civilizations don't last long. Advanced civilizations may inevitably self-destruct, nuclear war, environmental collapse, or there could be a great filter, a barrier that stops life from reaching advanced stages. The great filter is the idea that catastrophic events, either man-made or natural, cause intelligent life to be extinguished on habitable worlds. It's not clear if we have already passed this filter, or we are yet to reach it. But in 1961, Frank Drake created the Drake equation. How many alien societies exist and are detectable? Here's the equation. The number of civilizations in the Milky Way galaxy whose electromagnetic emissions are detectable. The rate of yearly star formation in the galaxy. The fraction of those stars with planetary systems. The fraction of stars that could support habitable planets. The number of planets that can potentially support life. The fraction of planets that actually develop life at some point. The fraction of civilizations that emit detectable signs of their presence. The average length that a civilization exists. The Drake equation aims to estimate how many intelligent civilizations exist. The Dark Forest Hypothesis. The Dark Forest Hypothesis, from Liu Cixin's sci-fi novel The Dark Forest, offers a possible reason why we haven't encountered aliens. They're hiding to survive. It compares the universe to a dark forest, where every civilization must stay silent or risk being attacked. The fear is that any contact could lead to conflict over resources or territory. To protect themselves, advanced civilizations may avoid or eliminate potential threats, explaining the silence of the cosmos. What is the relationship between the Dark Forest Hypothesis and the Fermi Paradox? The Fermi Paradox highlights the contradiction between the high chance of alien life and the lack of evidence. In this view, the universe is a dangerous place where staying hidden is key to survival, which could explain why we haven't made contact. What is the argument against the dark forest hypothesis? The dark forest hypothesis faces criticism for several reasons. First, with today's advanced communication and detection technologies, it seems unlikely that a highly developed civilization could remain completely hidden. Second, the idea assumes all intelligent life is hostile or fearful, ignoring the possibility of peaceful civilizations that might seek contact. Lastly, the theory doesn't explain the lack of traces from extinct civilizations, such as megastructures or space probes, which we would expect to find if such civilizations had ever existed. In the 1970s, we tried to learn more and more about these civilizations. In 1972, we sent a spacecraft to Jupiter, Pioneer 10. In November 1974, Earth beamed this image, called the Arecibo message, toward the globular star cluster M13. Its binary message informs alien societies about Earth, a counting scheme of 1 to 10, white, the atomic numbers for hydrogen, carbon, nitrogen, oxygen, and phosphorus, which make up DNA, purple, the chemical formula of the 4 purines and pyrimidine bases that make up DNA, green, an image of the DNA double helix, and AB estimate of the number of nucleotides, blue and white, respectively, a stick figure of a human being, red, our average dimensions, blue-white, and the human population of Earth, white. A depiction of the solar system, indicating that the message is coming from the third planet, yellow. A schematic of the Arecibo Observatory and its dimensions, purple, white, and blue. The multiverse. The idea of a multiverse, that our universe is one of many, is taken seriously by some scientists and explored in fields like quantum mechanics. The many worlds interpretation suggests that all possible outcomes happen in separate, parallel universes. Physicist Paul Halpern talks about these ideas in his 2024 book, The Allure of the Multiverse. He explores things like extra dimensions and how they could change the way we think about science and life. What exactly is a multiverse, anyway? There are two main types of multiverse ideas. Cultural. People imagine alternate versions of their lives. What might have happened if they made different choices? Scientific. These ideas are based on physics and split into two main concepts: the quantum multiverse and the cosmological multiverse. The quantum multiverse was addressed in 1957 by a young graduate student, Hugh Everett III, with the many worlds interpretation. He speculated that different possibilities split into different universes, and that humans experience multiple realities but don't really know about their doppelgangers. The cosmological multiverse is the idea that a process called inflation, a rapid expansion that likely happened just after the Big Bang, can happen not just once, but many times in different places. Because inflation is thought to be easy to trigger, it could be creating new universes all the time, each with its own version of reality. What are the properties of this universe that make physicists think a multiverse might be a correct interpretation of reality? The fine-tuning problem highlights how the physical constants of our universe are perfectly set for life. Physicist Brandon Carter suggested in the 1970s that we may live in one of many universes, most of which couldn't support life. So where do all of those other Earths exist? MIT's Max Tegmark describes different types of multiverses. A Level 3 multiverse comes from the many worlds interpretation of quantum mechanics, where all possible outcomes happen in branching realities. In contrast, a Level 2 multiverse comes from cosmic inflation theories, where each universe may have different laws of physics. Is there any direct evidence suggesting multiverses exist? The idea of infinite bubble universes helps answer deep questions, but nothing concrete. Some scientists see the universe's fine-tuning as chance, while others think we live in one of many universes, each with different laws. Will we ever know if our universe is just one of many? The multiverse is predicted by some testable theories, so confirming those theories could indirectly support its existence. As physicist Tom Siegfried points out, just because we can't test it now doesn't mean it isn't real. We may simply not yet know how to test it. Thanks for watching this far. See you next time. Don't forget to subscribe to the channel if you liked.